So we finally moved on to logarithms, and when we're looking at logarithms, we generally start by looking at logs to base 10. Okay, so in the olden days, one of the main reasons we learned base 10 first is because our calculators could only calculate logs to base 10. Right? Nowadays we can calculate to any base, right? And obviously this made learning to change logs back in the day very important. Now, it is nice to learn logs to base 10, and we'll explore the reasons why in a bit. So before we even think about logarithms, let's think about an exponential function, and we can think of this function f of x equal to base 10 to the power x. Okay, and another way of saying that is we're looking at the function y equal to 10 to the power x. Now let's consider if we were trying to solve 10 to the power of x equal to 6. Right? The idea is we're asking what value of x would give us 6. And we could just try some values. So we could try x equal to 1 and see what we got. So we could say 10 to the power of 1, right? And that would give us 10. That's too big. So let's try a smaller value. Let's try x equal to 0. So we could say 10 to the power of 0, and that would give us 1. And they were too small. However, you can say that the value we're looking for is somewhere between 0 and 1. And with a bit of trial and error, we could get a figure pretty accurate. And let's say we got a figure that was about 0.78. Right, so with a bit of trial and error, we could go 0.5, we could go 0.7, and so on, and we could plug in numbers until we got fairly close. Right, another way to try and solve this problem is to think, right, well, we know what the exponential function looks like. So here's the graph of y equal to 10 to the power of x. It's a standard exponential function. It goes through 1 at the y-axis, right? And the way we usually look at the exponential graph is we'll input x coordinates and it will produce y coordinates. However, we can use this to our advantage. We can say, well, actually we want to consider what value for 6, right? What solution of 6, what would the input value have been? And we can drop that down, and you can see we get fairly close to the value that we had previously guessed, which was around 0.78. Now again, this is not as accurate, right? We'd still be rounding or would be approximating what the value for x is. That would give us exactly 6, right? However, the graphs taught us an important thing. Now, if we think about the function y equal to 10x, generally we would plug in x values and the graph would give us solutions or y values, right? And when we start thinking about what kind of input values produce output values, right, what we're actually thinking about is the inverse function. Okay, so let's consider some inverse functions that we've already dealt with. Okay, the two easiest ones are addition and subtraction. So if we had a function that added 1, its inverse would be the function that subtracted 1. Okay? And visually we can represent those as two straight lines on the Cartesian plane. Okay? And we'll notice that because they're inverse functions, they are reflective about the y equal to x line. Now we could say the same thing about multiplication and division. So here we have 2 to the power of x, so times 2, and here we have x over 2. Right? Both of these are also straight lines. One has a gradient of 2, the other one has a gradient of half. And again, we can see they are reflective about the y equal to x line. Now, when we consider what we're talking about today, logarithmic functions, right? They are just the inverse of exponential functions. Okay? So if we had to consider our exponential function, the logarithmic is just an inverse of that function. Right? It's reflective about the y equal to x line. So now that we know what logarithms are, right, they are simply an inverse of an exponential, let's look at how we can convert exponentials into logarithmic form. So the first thing we need to do is we need to identify the parts of the exponential. Okay, and we'll start with the base. So here's the base. This is the, well, we can call it one of three things. Either we can call it the exponent, the power, or the index, right? They all mean the same thing. And this figure on the right here doesn't really have a name, but let's call it the value. Okay, in other words, if I raised 10 by some power, it would produce some value. Now, when we write this in logarithmic form, right, the first thing we're going to do is we're going to make the exponent the subject of the formula. Okay, so we're going to write x over here. And the next thing we're going to do is we're going to equate it into a log, right? And this log has a base 10, which we write as a subscript, so just below the log. And we place the value over here. Okay, so if we had to again identify the components, the exponent has now moved to the subject. The base has moved here as a subscript of the log, and the value has moved next to the log. Right? So this is how we rewrite an exponential into a logarithmic. Right? And in essence, all we have done is we've made the exponent the subject of the formula, which is good because we want to solve for the exponent in this case. Okay, so let's go back to our example of 10 to the power of x equal to 6. Okay, so we can change this into logarithmic form, so we can make the exponent the subject of the formula. So here's the exponent, here's the base, here's the value. So we start off by making the exponent the subject of the formula. We write a log. We keep the base stays the same, so that the base that was from the exponent is the same base for the log, and the value goes next to the log. Okay, and we can punch this into our calculator, right? If we're working with base 10 logs, we can just use the log button. If you don't see a number next to a log, it is implied that it is base 10. Okay, so on your calculator, you just push log 6, and it will give you 0.77815, etc., which we can round to 0.778 if we want. So this is the number that would then be that you could raise 10 by to give you 6. Right, now just like when we studied exponents, we had some rules. When we look at logs, we also have some rules that we need to follow. Okay. So if we have some function y equal to 10 to the power of x, because now we're looking at base 10 specifically, then we could rewrite that as x equal to log base 10 y. And what we're asking is, what do I raise the base 10 by to give me y? Right? So if we have a look at this simple example, log base 10 of 100, the question we should ask ourselves is, what power do we raise 10 by to get to 100? So what power do I raise 10 by to give me 100? And the obvious answer is 2. So that means that log base 10 of 100 is equal to 2, right? Because we have to raise 10 by 2 to get 100. Now, if we consider y equal to 10 to the power of x, when we look at inverse functions, what we do is we remap x and y. So if we had to remap x and y, we would get x equal to 10 to the power of y. And what we want to do now is resolve for y. Y now happens to be the exponent. Here's the base, and this has now become the value. Okay, so we've created the inverse function. We're going to resolve for y. So when we change to logarithmic format, we make the exponent the subject of the formula, equal to a log with the same base, and we put the value next to the base. Okay, so these two things are what we call the inverse functions. Okay, if you had to put a value for x into y equal to 10x, if you took the solution and put it into y equal to log base 10 of x, it would return you back to your starting x value. Okay, now this is quite different from y equal to 10 to the power of x, right? If we convert this into logarithmic form, just like this, where we make the exponent the subject of the formula, right? These are not inverse functions. These are two equivalent statements or equations, right? And what we mean by equivalent is it's the same way of writing the same thing, or a different way of writing the same thing. Okay, these two things are exactly the same. They're just written with a different thing as the subject of the formula. Here the value is the subject, and here the exponent is the subject. Now, using that simple knowledge, we can come up with two very important log identities, right? Tricks that we learn about logs that sort of help us to simplify them later on. So what we're going to do is we're going to start off with two simple logs. So we're going to say, let's have 10 to the power of x equal to 10 to the power of x. Okay, now logically, intuitively, we can see that these statements are exactly the same. But what we're going to do is we're going to change this into a log. And how we're going to do that is we're going to say, this is the base, here's the exponent, and this thing here, this whole thing here is the value. So let's change that into log. So what we do is we make the exponent the subject of the formula, and we write it as a log, and we keep the same base, and then we write the value next to that. And here what we've done is we've come up with one of the most simple log identities. So if you have a look here, if you have a log to some base and the value of that base is the same, the value is the same as the base, it can be simplified into the exponent. Okay. The next identity comes from this. So if we have log base 10 of x, and once again we'll make it log base 10 of x, except this time what we're going to do is we're going to change, this is now in log format, and we're going to change this back into exponential format. So here we have the base, here we have the value, and here we have the exponent. Okay, if we imagine this is in log format, let's change this back to exponential. Okay, so what we do is we'll write to base 10. Now we need to raise to the exponent, and this is equal to the value. And once again, we've come up with a simple a log rule. All right, so if you have a base raised to a log with the same base, right, it's equal to the value of that log. Okay, and we'll use these when we are simplifying log identities later on. Okay, let's just have a look at a simple little idea here. Okay, again, here we have a log base 10 of a couple of numbers. They're all powers of 10. And again, the important thing to remember when you're looking at logs is you want to ask yourself, what am I raising the base by to get the value? Okay, and that really does help you to work out what kind of a number we're trying to produce. Okay, so if we consider log base 10 of 10, what we're asking is, what do I raise 10 by to get 10? And the answer is 1, okay, because anything to the power of 1 is itself. If we move on, we're asking, what do we raise 10 by to get 100? And the answer is 2, okay, because 10 to the power of 2 is 100. And if we continue to the right, we raise 10 by 3 to get 1,000. Right, now let's go the opposite direction. Here we're asking, originally, like I said, what are we raising 10 by to give us 1? Now if we think about our exponent laws, there's a number that if we raise anything by that number, it's 1. And that happens to be 0. Okay, so if you raise any number by 0, it becomes 1. Right, now here we're asking, what do we raise 10 by to get 0.1? So what is 0.1? Well, 0.1 is another way of writing 1 over 10. Okay, and you'll notice the 10's now jumped to the denominator. Okay, so how do we get the 10 to move down? Well, the way we do that in index notation is we would say minus 1. Okay, now remember what a log is it's solving for an exponent. So when we get a negative value or a negative exponent, that just means that it's pushing something either to the denominator or up to the numerator. Okay, and here again, what are we raising 10 by to get 0.01? This is just another way of writing 1 over 100, okay, which is just another way of writing 1 over 10 squared. So how did we get the 10 to move down? Well, we had to put a minus. How did we get the 10 to become 100? We had to square it, so the answer is minus 2. All right, let's look at some examples. Right, here we're being asked to convert 10 to the power of x equal to 45 to logarithmic form. Okay, now there are two ways to do this. Okay, the first way is by identifying the different parts of the log. Okay, so here we can identify, here's the base, here's the exponent, here's the value, right? And simply by rearranging into log form, we can convert this into log form. So we start off by making the exponent the subject, which was x in this case, equal to a log. We keep the same base, and we put the value next to the base. Okay, so this is the most intuitive way of converting logs. The other way of converting logs, right, is using a technique, well, when we're converting from exponential to logs, is something where we log both sides. So what we're going to do is we're going to say we have 10 to the power of x equal to 45, right? And what we're going to do is we're going to log to base 10 on both sides of the equation. Okay, so this is what we're saying is log 10 of this must be equal to log 10 of that, meaning that two things that are highlighted must be equal to each other, which is what we started off with, so we haven't really changed the equation much. Okay. Right, so from here, what we notice is we have got the condition that we looked at before, right? So this is the one where we have, if we have a log to base 10 and the value is 10, we can simplify that into the exponent. So in our case here, this means that this thing on the left-hand side can be simplified into x, and on the other side we have log 10 45. Okay, same as method 1. Okay, except this, we took logs on both sides in the second method. Same procedure or same answer, just a different way of getting to the answer. Okay, part B says solve now. Okay, you want to find the value for x. In order to find the value for x, we needed to make it the subject of the formula. That's what we've done in the first step. So we've got x equal to log of base 10, 45, and you simply punch that into your calculator. You can push the log button instead of having to use the one with the base, right? So log means base 10, 45, and we'll get 1.653, etc. And we want 3 significant figures, so that's 1.65. Okay, in this example, we are being asked now to convert log base 10 of x equal to 2.9 to exponential form. Okay, so this is in log form, and we want to go back to exponential form. So again, there's 2 methods. Right, the one is the intuitive one, where we're going to identify the parts. So here's the base, here's the value, and this is the exponent. Okay, so we're just going to switch things around back into the exponential form. So an exponential has a base, which is 10. We're going to raise it to its power, and that must be equal to some value. So here we've rearranged and changed the subject of the formula. The second method, just like with when we convert to logs, we are going to take our equation, log base 10 of x equal to 2.9, and what we're going to do is we're going to raise both sides into an exponential with base 10. Okay, so in other words, we're going to say 10 to the power of log base 10x must be equal to 10 to the power of 2.9. So this is very similar to when we used to solve exponential equations. If we had 2 to the power of x plus 1 equal to 2 to the power of 3x plus 4, if the bases were the same, we could drop the bases and just equate the exponents. Okay, so that's exactly what we've done here. We've just raised to a base, right? Because the bases are the same, we could technically now drop but we want to have these equated. And the reason we want that is because we want to make use of this rule over here. Okay, if we have an exponent and it's raised to a log with the same base, we can simplify that into the value, right? That's the rule that we looked at over here. So if we have a base or an exponent raised to a log with the same base, we could see that it was equal to the value, right? That means that in this example here, we can simplify the left-hand side into just x, which is the same as method, right? Okay, part B says solve, right? To solve, we need x to be the subject of the formula, 10 to the power of 2.9. We just stick that into our calculators now, 10 to the power of 2.9, and we'll get 794.32, etc. To 3 significant figures gives us 794. Here we have one final example, and here generally you're going to be asked to find these without a calculator. Okay, so once again, we're being asked, what do I raise 10 by to get me this 100,000? So what we can do is we can convert 100,000 into something that is base 10. Right, so this is the same as saying log base 10 of 10 to the power of, we can intuitively work out that this is going to be 5. Right, and once again, we have this rule where if we have a log with a base and the value is the same as the base, we can simplify that into the exponent, right? And so this is just equal to 5. And logically that makes sense. 10 to the power of 5 gives us 100,000. Okay, here we have log base 10 of 0.001. Here we're asking, what do we raise 10 by to get 0.001? Okay. So what we can do is we can convert 0.001. We can say this is log of 10 to the power of, well, that's 1 over 1,000, which is the same as log base 10 of 1 over 10 to the power of 3, which is the same as log base 10 of 10 to the power of minus 3. And once again, here we have a log. The base and the value are the same, and so we can simplify into the exponent. And finally, here we have log base 10 of 100 square root 10. What we're going to do is we're going to try and simplify this into base 10. So we'll say log base 10. 100 can be written as 10 squared. And the square root of 10 can be written as 10 to the power of a half. Okay. Using our index laws, we can see we're multiplying two numbers with the same base, so we can add their exponents. So we'll have log base 10, 10 to the power of 2 plus a half is 2.5. And once again, here we have a log. The base and the value are the same, and so we can simplify this to 2.5. So 10 to the power of 2.5 is the same as log 10 of 100 square root 10.